Let's get started. So just the final reminder of the exam, which you've been warned about, is coming up on Friday. I've written it, so I know what's on it now, and I think you'll find it interesting. Right, interesting. We're still tweaking a little bit the office hours. Paul Cothene, one of the GSIs, has been offering office hours on Tuesdays from 4 to 5, but so far he hasn't gotten any customers, so that apparently isn't a very popular time. He's willing to shift the schedule around, and so he's thinking now about Tuesday or Thursday from 11 to 12. How many of you would take advantage of that? Okay, do you have a preference for Tuesday or Thursday? Thursday? That's tomorrow? Okay. Think long term, though. I mean, Thursday. And then he would be willing to do other office hours, but by appointment. Okay, so let's assume it'll be Thursday, 11 to 12, in room 4126, and then others by appointment. Okay. That's it. And so the exam will be Friday. I will give you a new homework assignment on Friday, because we're not stopping, okay? And what that's going to cover is the material we're doing this week, which has to do with gamma decay. That's in Chapter 3. And next week we're going to start beta decay. So the homework assignment I'm intending to give you on Friday will cover both gamma and beta decay. Okay? Okay. Now before we get serious again, I have one more probability brain teaser for you. Okay. So this is one that came out of an airline magazine. You flip two coins, 2 quarters, let's say. They're normal, fair coins. And after you flip them, you observe one of them and see that it's a head. What is the probability that the other one is also a head? It's another probability one, like the ones we did before, just a little wrinkle. What's your, okay, go ahead.
You observe that one of them's a head, like is the one
You observe only one of the 2 coins. So you get to see one of them and you happen to see that it's a head. You haven't seen the other coin yet. And the question is, what is the probability that that's also a head? What's the first reaction you have when you hear this? Right, 50-50, right? Because each one has a 50% chance of coming up ahead. It turns out that's wrong. Okay, and it again has to do with just thinking about probabilities. So if you flip 2 coins, what are the 4 possible outcomes for the heads-tails business? Okay, so it could be heads-heads, or it could be tails-tails, or it could be this one's a head and that one's a tail, or it could be that one's a tail and this one's a head. Right? Okay, so you've done an experiment. You flipped the 2 coins and you've measured that one of them's a head. So that rules out this possibility. It can't be that one. Therefore, there are 3 possible outcomes left. And you've determined that one of them is a head. Okay? But in 2 of the 3 remaining outcomes, there is only one head, and you've happened to have seen it. So there's only one possible outcome where the other guy can be a head, namely this one. And the probability of that is 1 out of 3. Okay, a little tricky. And the reason I'm doing this is these kind of things are going to come up over and over again in our physics. You need to think about probabilities, okay, and how you handle them, and when there are independent outcomes and when they're not. So it's not totally unrelated to the class, but nearly so. Okay, so let's get back to gamma decay. And we left off on Monday with a discussion of these things called nuclear isomers. These are states where you have 2 nearby levels, sometimes the ground state and first excited state, but not always that case, where they're not very far apart in energy, but they're very far apart in terms of angular momentum. And what I was arguing the other day is that it's difficult for a photon to carry away very much angular momentum, and as a result you get situations like this one, where the 0+ level, which is 228 keV above a 5+ level, prefers not to gamma decay at all. Instead, it beta decays rather than gamma decaying because 5 units of angular momentum is simply too much to carry away. Similarly here, you have either 7 or 8 units of spin difference, very little energy difference, and so this state essentially lives forever. And these are not isolated examples. It turns out there are isomeric levels throughout the chart of the nuclides, and this is a chart illustrating where they occur in terms of Z and N. And while they're not uniformly distributed across the chart, there are lots of them. So this is not an isolated phenomenon. More often than not, it occurs in odd nuclei, but not always. Because you've seen in these odd nuclei, you can get very different spin configurations depending on whether you're adding the spins parallel or anti-parallel, and they're often not very far apart in energy, and that leads naturally to these kind of isomeric transitions. So it's not so unusual to see an excited state of a nucleus living seconds or minutes or hours, even though when you go through those Weisskopf estimates, you find that they should all decay with tiny fractions of a second. It's not necessarily true. Okay. Now, what I've said up until now about excited states is that they generally decay by emitting gamma rays, but it turns out there's a competing process. It's called internal conversion. And the idea here again goes back to the fact that we don't have isolated nuclei usually. Normally we have atoms that have a full complement of atomic electrons around them. And especially if you have some heavy element, uranium or plutonium or lead, the innermost electrons are bound by a very large amount of energy, on the order of 100 keV or so. And if you think about the quantum mechanical wave function that describes at least the innermost electrons, they're spending a fair bit of their time inside the nucleus. Okay? So that picture that you saw in your high school chemistry books of the electrons orbiting, I told you was wrong, and it's very wrong in this situation because they're actually sitting in the nucleus part of the time. And while they're in the nucleus, they can interact with the nucleus, okay? And one of the processes by which they do that is called internal conversion. The idea here is that you have a nucleus that happens to be sitting in an excited state, and rather than emitting a photon, it takes that excitation energy, the difference between its energy and the level to which it's going to make the transition, and it transfers that energy directly to an atomic electron. Okay, an electron that just happens to be sitting in the nucleus at that instant. And instead of emitting a photon, then you emit an atomic electron, and the energy of that atomic electron, and now I'm talking about the kinetic energy of that atomic electron, T sub E, is equal to the excitation energy of the level minus the binding energy of that particular electron. Okay? And this is an example of an electron spectrum from one particular isotope, lead-212. And what you see, there's sort of a broad continuous distribution, in fact, two of them. Those have to do with beta decay, which we're going to spend more time talking about next week. But these discrete peaks that you see here correspond to particular excited states of this nucleus decaying and transferring that excitation energy to an electron. And the reason you get so many different levels or lines here, you probably can't read it from the back of the room, but they're labeled by the orbital in which the electron was sitting when it got ejected. So this says K, this says L, this says M, N, O, and so on. The more tightly bound the electron is, the more energy you have to provide to liberate it from that orbital. And so since you have a fixed amount of excitation energy to start with, you end up with a lower energy electron the more tightly bound it was. The outer electrons, the L's, the M's, the N's, were less tightly bound, therefore they come out with more kinetic energy. So this is a competing process to gamma decay. And it's not a two-step process. It's not true that what happens is a gamma ray gets emitted and that gamma ray gets absorbed by the electron and then the electron is emitted. We'll see later on when we talk about the photoelectric effect that the cross-section for that to happen is way too small to explain what you observe. This is a direct transfer of nuclear excitation energy to an electron. Okay? And when we talk about electron capture decay next week, we'll see a similar phenomenon where you get a beta decay happening because an electron is spending time inside a nucleus. Question? Okay. So here's a picture again. Here's our initial state I, final state F. Last time I said it would gamma decay. Here I'm saying it can internally convert. And this is an example. Yes?
I do have a question.
Sure.
So we said that the half-lives of all of these are not really affected by external conditions.
Uh-huh.
So what if you strip some electrons off?
Very, very good. Okay, so this is a counterexample to that. Yep. What you're saying is exactly right. Here I've got a process which depends intimately on the density of electrons right inside the nuclear volume. And anything I do to change that will affect these decay rates. So you're absolutely right. The extreme case is, imagine I could strip all the electrons off an atom. So now I have a bare nucleus sitting there. There are no bound electrons at all. It simply can't internally convert in that case. And there are very nice examples of that. where people have studied this effect, and you can do it, okay? Now that's an extreme situation where you rip off all the electrons. You can imagine ripping off a few electrons, and even if you remove just the outermost electrons, that will affect the innermost electron orbits because of what's called electron screening. And so you can produce measurable effects that way. That's exactly right. And when we talk about electron capture, you'll see similar things.
And so, I guess part of what I'm wondering then is, if this does that make it more likely to get rid of the other ones?
Well, not more likely. These are independent processes. They're all going on. And I guess what I would say is if, for example, you had a situation like I'm showing here, and you somehow, let's say, stripped away all the electrons and therefore turned off the internal conversion decay, the gamma decay would still happen, but at the same rate it was always happening. You don't alter that rate just because you've done something over here. I mean, it's kind of like that silly diagram I had a few weeks ago where I had a bucket with holes in it. You know, the water's coming out of each hole at a certain rate. If I close one of the holes, it doesn't change the rate of the water coming out the other hole. And that's kind of what's happening here. Okay, so these two things are going on in competition, but independently of one another, if that answers your question. You know, in general, you can have many different mechanisms that would allow that state to decay. And usually the gamma decay rates are totally independent of environmental factors, but internal conversion, electron capture, some of the other processes can be affected, but the gamma ray decay rate will still go on. Okay, so it is a competing process, and so if I wanted to know the total decay rate of that state, I have to add together the rates for the gamma decay and the internal conversion. And those formulas we wrote down the other day, those Weisskopf estimates, only considered gamma ray emission. They did not include this. So what is usually defined as a quantity called the internal conversion coefficient, which is a measure of how likely it is for the excited state to decay by emitting electron versus emitting a gamma ray. And so this internal conversion coefficient is called alpha, and it's simply the ratio of the electron decay rate to the gamma ray decay rate. And the total decay rate then, since it's the sum of the electron decay and the gamma decay, we can rewrite in terms of just the gamma decay rate times 1 plus this quantity alpha. Okay? Now, alpha itself is a slightly complicated object because it depends on which electron orbit you're talking about. So the alpha, which appears here, is actually the sum of internal conversion coefficients for all the different electron orbitals that in principle could contribute. So the nomenclature here is K refers to the 1s orbital, L refers to the 2s and 2p, M is the 3s and 3d. And what we're saying is that you can have a transfer of this nuclear excitation energy to the innermost electron, in which case you'll kick out a K-shell electron, and there's some probability for that. Or, in principle, you could do it with an outer shell electron, and there's a different probability for that. And that's what these internal conversion coefficients are measuring. Normally, the electron which is spending the most time in the nucleus is the 1s electron, the most tightly bound. And therefore, in general, the alpha K will be the largest internal conversion coefficient. And generally, they go down as you move further out because the further out electrons obviously are spending less time in the nucleus. There's a smaller probability that the excitation can be transferred to them. What I just said isn't always true because there are situations where this difference in energy between the two states is less than the binding energy of the innermost electron. So, for example, in lead or uranium, like I was saying, that inner electron is bound by 100 keV or so. And if you have a transition whose energy is less than that, then obviously you don't have enough energy available to kick out the inner electron. You're forced to kick out further and further out electrons. So if you have enough available energy, in general, this will be the largest, but you have to be careful in looking at the energy of the transition compared to the binding energy of the electron you're talking about. Okay, so it turns out that the same nuclear physics which is involved in predicting gamma ray decay rates is involved in predicting these internal conversion coefficients. Okay, it's the same nuclear matrix element. What matters and what allows you to calculate the ratio of the internal conversion to the gamma decay has to do with the probability of the electron being inside the nucleus. So it depends on the square of the electron wave function, essentially at the origin. It also depends on the z of the nucleus, which obviously affects the wave function. It depends on the orbital angular momentum that the electron has to carry away. And as I was indicating, it depends on the excitation energy of that state. So these are formulas analogous to what we wrote down for the Weisskopf estimates, but now for internal conversion coefficients. And there's an internal conversion coefficient you can write down for the electric type transitions, and there's a separate one for the magnetic type. Okay? And the important thing is not to memorize these formulas. Okay? Obviously, if you had to do a calculation, you'd be given these, but to see sort of qualitative features of it. So for example, there's this z cubed dependence here. Okay? So that tells you right away that this is going to be most important for the highest elements. Why is that? Because those are the elements where you've got electrons spending a lot of time near their nuclei. It's going to be inversely proportional to the gamma ray energy. Okay? The larger the energy, the less likely this is going to happen. And it's going to depend on the angular momentum that the electron has to carry away. Again, because the electron has a difficult time carrying away very much angular momentum, it's going to be hard for it to make big difference in L values. And these formulas are valid for this range of gamma ray energy. Okay? If you get way beyond that, the formulas are not so good. But they're just qualitative guides to have in the back of your mind. These are calculations based on those formulas for different kinds of transitions, depending on whether they are electric or magnetic, and depending on the multipolarity of the transitions. And again, there's just lots of numbers here. But for example, if you look over here, this is the energy of the transition. This is the internal conversion coefficient for the k electrons, the innermost electrons. And the point is that as the energy goes up, the probability goes down, as I said before. Depending on the multipolarity, there's a big difference. M1s are smaller than E1s, smaller than E2s, and so on. And you can also see that the probability for the conversion goes up as you go to higher and higher Zs. So that lead 212 example is a good one. Okay, so just qualitatively then, because of the Z cube factor, you expect internal conversion to be more important in heavy nuclei. It's going to decrease with increasing gamma ray energy. It's going to increase with the multiple order because it's relatively easier for an electron to carry away angular momentum than it is for a photon. Why would you expect that? What's one difference between an electron and a photon? It has a mass. Okay, that helps in terms of carrying away angular momentum because it's R cross P. And so the electron has a little bit more momentum and therefore has an easier time carrying away more angular momentum. And the other feature I should have mentioned, so there's this n cubed dependence. That's the principal quantum number that defines the wave function of the electron. And the higher that number is, the smaller the probability the electron is at the origin, and therefore the smaller the probability of internal conversion. Okay. So a related phenomenon associated with this is that, remember the other day we were talking about decays of photons, and that you could not have a single photon decay between a 0 plus and a 0 plus level. Okay, if I had an excited state that had spin-in parity 0 plus, and the final state was also 0 plus, a single photon can't do that because the photon carries away a minimum angular momentum of 1 unit due to its intrinsic spin. So that decay can't happen by photon emission, but it can happen by electron emission. Okay, that rule is not followed for electrons. And so there's an example of this with germanium-72. It turns out it has an excited 0 plus level, 691 keV. So I think this is another counterexample to my general rule of thumb that even nuclei are going to have 2 plus first excited states. Well, here's one where it isn't true. It's rare, but this is an example of it. So this 691 keV level has a 0 plus first 0 plus spin. It can't emit a gamma ray. However, it can emit an internal conversion electron. And if you calculate the rate for this process, it turns out you can explain the decay rate being 0.42 microseconds. Okay? The 2 plus level, on the other hand, is going to decay by a single photon. It's an E2 photon, carries away 2 units of angular momentum and no parity change. And the Weisskopf estimate for that is shown here. You predict a lifetime of 7.8 times 10 to the minus 11 seconds. It's a bit longer than that, but not terribly far off. And just to try to show you that internal conversion is not a rare process, here's a nucleus you've seen before. This is hafnium-180. So getting ready for the exam, what kind of excitation spectrum is that? Rotational. How do you know that? Well, it's got the 0 plus ground state, first excited state 2 plus. The levels keep getting further and further apart, and you have this nice sequence 0, 2, 4, 6, 8 in terms of spin. We talked about the gamma rays that were emitted between the transitions, between the states, and I showed you those nice discrete gamma ray spectra where the gamma ray energies monotonically go up in energy. It turns out those levels can also internally convert. So instead of getting a 93 keV photon emitted, you can get an electron emitted with 93 keV minus the binding energy of that electron. So if it came out of the 1s or k shell, that binding energy is probably, 70, 80 keV. So you end up with a 20 or 15 keV electron emitted instead. And similarly, when this one decays, you could get a 215 keV minus whatever electron binding energy you had. So what's being shown up here is for each of these transitions, that is, the transition is the difference in energy between the initial and final states, the relative intensity of gamma rays, and the way they've done it here is they've arbitrarily defined this 332 keV transition to be 100. So they've just normalized all the transitions with respect to that one. And what's being shown over here are the internal conversion coefficients for each of those transitions. And so, for example, if I look at this 57 keV up here, what it says is that there is no K conversion for that particular electron. The first internal conversion coefficient that's listed is L, and that's because of this thing I was saying a minute ago, that the innermost electron, the K electron in hafnium, is bound by more than 57 keV, so you can't internally convert on that electron, but you could internally convert on an L electron or an M or an N, and the probabilities for those decrease as you move out in orbitals because of the probability for the electron to be in the nucleus keeps falling off. Similarly, if you go to the 93 keV, so that's this transition, now you're above the binding energy of that K electron, and so you can internally convert on that, and you see a measured internal conversion coefficient of 1.1. And similarly for the other transitions, okay? And you can calculate these using those formulas, and the calculations agree reasonably well with what you see experimentally. So internal conversion is always going to be a competing process to gamma ray emission. So this is the gamma ray emission spectrum of the hafnium-180, just that diagram I showed you a second ago. This is another one. This is silver-108. It's another example. You have a bunch of different E2 gamma rays that come from either the beta plus decay or the beta minus decay. And each one of those transitions can either decay by a gamma ray emission or internal conversion. This was a figure out of Crane's book, and in those days they thought this excited state up here, this 6 plus level, notice here this is an isomer. It's a 6 plus level that's something like 30 keV above this 2 minus level, which is 79 keV above the 1 plus level. So you have a large spin difference and little energy difference. That state has a hard time decaying, so it's an isomeric level, and the thought was the half-life was 127 years. It's actually a lot longer than that. So here is a gamma ray spectrum as well as an electron spectrum taken from that silver-108 decay. So down here you see the gamma rays. Just go back for a second. So 633, 434, 614, 723. Those would be the gamma ray energies, and those are what you see here. But each one of those transitions can also internally convert, and so you get a series of electron lines. So for example, from this one 434 keV transition, where you see one gamma ray, you end up with 2 or 3 different electron lines, again, depending on which orbital the electron was converted from. So the lowest energy one is where you convert from the K shell. The next one is the L shell. If you look more carefully, you'd see M and Ns as well. So these spectra can be fairly complicated, but they're useful. And just to show you that, in fact, these estimates of the half-life were wrong, this is some data that was recently taken trying to measure the half-life of that state, and we measured the gamma rays over a function of about 2 years, and we find that the half-life, instead of being 127 years, is actually 440 years. So it's an experimental science. Don't necessarily believe all those numbers you find in the books, but most of them are going to be right. Okay, so we've talked about internal conversion and gamma decay, and we've seen that the probabilities for both processes depend on the multipolarity of the transition, meaning if it's an electric dipole transition or a magnetic dipole, the rates for those processes are different. The question is, how do you tell what the multipolarity is? Okay? If you look at the excitation energy of the states, that doesn't necessarily tell you. And even if you know the initial and final spins and parities, that doesn't necessarily tell you. If you go back through the selection rules for both the magnetic and electric transitions, you'll see very often there are cases where you have a certain initial and final spin state, and there could be 2 or 3 or 4 different multipolarities that would connect those states together. And so we'd like to figure out a way, experimentally, to figure out what the multipolarities are. So one way to do it is to measure the internal conversion coefficients, because the probability for the internal conversion relative to the gamma decay depends very strongly on the multipolarity. So that's a good way to do it. And in a few weeks, we'll talk about the detectors that we use to do this, but we use magnetic spectrometers as well as ionization counters called silicon detectors. Another way to do it is what's called measuring the gamma ray angular distributions, or correlations. And again, we use a different set of detectors to do that. And the idea here is that when you have a gamma ray transition, it's not necessarily true that the gamma rays are emitted isotropically. It could be that there are, and we'll see reasons in a minute, why gamma rays are preferentially emitted in some directions versus others. And it turns out that's a function of the multipolarity of the transition. And by measuring those probabilities as a function of position or angle, you can learn something about the multipolarity of the transition. One thing you might think about is sort of an analogy between nuclear physics and atomic physics. So I think you probably studied in atomic physics the fact that there's something called a Zeeman effect, which means that if you have, let's say, a state of spin 1, we know that there are 3 z components of that angular momentum. Okay? The z component of that can be either +1, 0, or -1. Okay? Now, if I'm in a region of space where there are no magnetic fields, and now I'm talking about an atom, okay? Those 3 z components of angular momentum all have the same energy. Okay? And you can think of this in the atomic system as a nucleus with an electron orbiting it. And so you can think of it kind of like a current loop. Okay? And if I have no magnetic field, no external magnetic field, all 3 states have the same energy. But if I apply a magnetic field, now there's an interaction between that current loop and the external field. It's a mu dot B term, okay, which hopefully you've seen before. And so that splits this one level into 3 levels. And so I end up with 3 states that have slightly different energies now. And so in principle, if I wanted to determine the multipolarity of a transition, if I could select out one of those states preferentially and watch it decay, that would help me, okay, rather than having all 3 states contributing. So the question is, can I do that with nuclear levels? So now I'm switching from the atomic case to the nuclear case. Now I'm saying this is a nucleus that has spin 1. It will still have 3 z components of angular momentum. Can I apply a magnetic field and split them in such a way that I could observe it? Well, the answer, unfortunately, is no. And here's the arithmetic. So the splitting I would get, this delta E that I would get by applying an external field, depends on this product of the magnetic moment, mu, times B. We talked about magnetic moments a few weeks ago, and the typical unit for them was 1 nuclear magneton. Okay, and you can go back and see what the definition of that is. And now I apply, a sort of big magnetic field, the kind of biggest one I could get, which might be something like 10 Tesla. That's 10 to the 5th Gauss. That's a very strong magnetic field, but something we can do. And if I just plug in the numbers, then mu dot B in energy units turns out to be about 3 times 10 to the -7th electron volts. So in fact, I can split them, but by such a small amount, experimentally, I can't see that. I don't have detectors good enough to see that kind of energy splitting. So in practice, I can't do this for nuclear cases. For atomic cases, yes, you can do it. The splittings are larger, and in fact, we have detectors that can see the atomic splittings very easily, but not in the nuclear case. So we're not going to be able to do it that way. The way you can do it, or one way you can do it, is what's called a gamma-gamma angular correlation. This is a little subtle, so I'll go through it slowly. And again, it's not going to be on an exam, but just to try to show you how we deal with these things experimentally and the kind of information you can get. So imagine you have a decay sequence like the one shown here. So you have a state, an initial state, this is called 0 up here, which has spin 0. Okay? It then decays to a state of spin 1, which then decays to another state of spin 0. So the spin sequence is 0, 1, 0. Okay? Now, if I am in a spin 0 state initially, there is only one J sub z component of that state, namely 0. Okay? But when a gamma ray is emitted, that gamma ray can lead to all three J sub z components of the intermediate state that has spin 1. In other words, I can go to the spin J sub z plus 1 state, spin 0, or spin minus 1. Okay? All of those are allowed. And then each one of them, when they decay, will ultimately end up in this spin 0 final state. Okay? But depending on which of these intermediate J sub z components I populate, I will get a difference in the emission probability for these two gamma rays with respect to each other. In other words, if I have a source that is sitting in that state 0, and I have two detectors, and I measure the first gamma ray, gamma 1, in the detector called detector 1, and I measure gamma 2 in the detector called detector 2, and I vary the angle between those two detectors with respect to the source, I end up seeing a probability distribution which looks sinusoidal. Okay? That's very typical of this kind of configuration. Okay? And from the shape of that and the amplitude of it, you can learn something about the multipolarity of the transition. And so let's just go through that a little bit. It illustrates some of the ideas we talked about in terms of gamma ray emissions. So we're considering this sequence where I'm going to assume initially that my gamma ray that goes from the initial state 0 to the state 1 happens to populate the J sub z component equals 0 there. Okay, that isn't the only one that can happen, but for this discussion I'm going to assume that's the one we've got. That turns out to be a dipole transition. Okay, 1 unit of angular momentum change, that's a dipole transition, and you end up with a characteristic dipole emission probability pattern. I showed you those diagrams the other day, that you don't get isotropic emission from a dipole. You get these things that look like sine squareds. So the Anger distribution of that first photon goes as sine squared. Now I'm free to define my coordinate system any way I like. So what I do is I define theta equals 0 to be in the direction that first gamma ray goes off in. So I define theta equals 0 to be in this direction, towards detector 1. Okay? If I do that, then there's no probability to emit a gamma ray in that direction. Okay? I can't have a gamma ray that populates a state of final z component 0 in that direction. So what that means is if I get a gamma ray in that direction, I must be populating the states of spin J sub z equal plus 1 or J sub z equals minus 1. If I'm in a J sub z equal plus 1 or minus 1 state, and then I decay to a spin 0 state again, which is the sequence I'm talking about here, it turns out you get an Anger distribution between the two gamma rays that goes as 1 plus cosine squared theta. And so you end up predicting on this sort of hand-waving argument that you get a pattern that looks like that. And the particular shape, this one, is only true if it's a dipole. If it were a quadrupole, each of these functions would be different. I would get a different shape. So the point is, by measuring that angle, gamma-gamma angular correlation, you can infer something about the nature of the multipolarity. In general, the formulas are going to be a bit more complicated. So for a general transition of unknown multipolarity, the angular distribution between, or the angular correlation rather, between the two gammas is going to look like this. There's going to be some constant out front. It's going to depend on multiples or cosines to the 2k, where k is going to depend on the multipolarity, the initial and final spins. Now here's an example that you've seen before. The other day we were talking about the decay of cobalt-60. So cobalt-60 was one of these long-lived radioactive species that beta decays, and we saw that it beta decays to an excited state of nickel-60. It turns out the beta decay feeds a level that has a spin imparity of 4+, which then decays to a state of spin 2+, and then that state decays to a state of spin 0+. I get two E2 photons, okay, electric quadrupole photons, each one of which carries away 2 units of angular momentum. But I have a very specific sequence. It's a 4+ to 2+ to 0+. So if I do an experiment, like the experiment I had pictured there, so I have two detectors, And I vary the angle between the two detectors. And I measure, let's say, this gamma ray in detector 1, and I then measure the probability to find this gamma ray in detector 2 as I vary the angle between them. This is real data that was taken showing the effect. So the way this is plotted, they've got data taken where the two detectors are at 90 degrees with respect to each other, and you measure a certain number of gamma-gamma coincidences, and you call that 1, and then you vary the angle. So you increase the angle from 90 degrees up to 180 degrees. So you're going from this kind of configuration to this kind of configuration, and you're just measuring the probability of getting both gamma rays. And what you find is it doesn't stay flat. It varies by almost 20% as you vary that. And that's because of the nature of this transition sequence, that it's two E2 transitions. And the way to think about it is that what's happening is when you have this beta decay initially, you start out with an equal population of all 9 different J sub z states up here, okay? 2J plus 1. So there are 9 J sub z values for that 4 plus level. But in the decay here, you preferentially populate different amounts of the J sub z equals plus 2, plus 1, 0, minus 1, minus 2. And when these decay, you get a different population. And so you end up with an unequal population of these J sub z states, which leads to this gamma-gamma correlation. Okay? So don't worry about the details of this. The basic idea is that experimentally, you have 2 ways to get a handle on the multipolarity. One is from the internal conversion coefficients, and the second is on gamma ray either Anger distributions or gamma-gamma correlations. Okay? And I'm going to call it quits on gamma decay there. So I'm happy to answer any questions, but I'll stop here, and then if we don't have any questions, we'll see you Friday. And I do have office hours from 2 to 3 today.